So you know the charge of proton is 1.6 into 10 to the minus 19 coulomb. Charge of an electron is minus 1.6 into 10 to the minus 19 coulomb. Charge of proton is positive, charge of electron is negative. Mass of proton is 1.007277 U, and mass of neutron will be 1.00886665 U, and your mass of electron is 0.00054866 U. So proton is positively charged, electron is negatively charged, neutron is neutral, and your mass of proton is smaller than that of the neutron, and mass of the electron is very less than that of proton and neutron. And your radius of an atom is of the order of 3 angstrom, and radius of a nucleus is around about 1.2 femtometer, or around maximum 10 to the 10 femtometer. So Niels Bohr has proposed the atomic model as shown in the screen. Here you can find that in the nucleus, protons and neutrons club together, and electron revolves around the nucleus in different orbits. So there is a mass energy equivalence, and Einstein proposed this equivalence, and it is popularly known as mass energy equivalence. So the masses of a particle are expressed in atomic mass unit, that is U, which I have discussed in the table for a neutron, electron, and a proton. And as per Einstein's mass energy equivalence principle, energy and mass are interconvertible and can manifest mutually, and both could be expressed in the same unit. In the classical mechanics, we have our mass in kilogram, milligram, such type of units, and energy in joule or org, this type of units. But according to Einstein's mass energy equivalence principle, your both energy and mass can be expressed in the same unit. So using the conventional definition of energy and mass, there is a relation. Energy is equal to mass multiplied by c square, where c is speed of light, that is 3 into 10 to the 8 meter per second. So the energy gain is accounted by the loss in mass in neutron physics or nuclear physics. So your one atomic mass unit is equal to 931.5 mega electron volt by c square, where your mass of proton is 938.273 mega electron volt by c square. And your mass of neutron is nothing but 939.565 mega electron volt by c square. So nucleus is represented symbolically as X superscript A subscript Z in the left hand side, where A stands for the atomic number, mass number, and Z stands for atomic number. And A is the chemical symbol of the atom. X is the chemical symbol of the atom. So let us represent uranium isotope. It can be represented as uranium-238-92. 238 is its mass number and 92 is its atomic number. Or you can just write uranium-238, where 238 is mass number and you will not represent the atomic number. and you can write it as U-238. Similarly, electron can be represented as 0e-1 and proton can be represented as 1p1 and neutron as 1n0. So your superscript represents the mass and the subscript represents the charge. So electron mass is very small than that of the proton and neutron, and it is placed as 0. And for proton and neutron, it is nearly same, and it is 1. And the charge of electron is -1. Hence, in the subscript, you can see that -1. And for the charge of proton is 1, so you have 1p. And the charge of neutron is 0. Hence, you have 10n. So you know what is nuclide, what is isotope, so on and so forth. You know what is a nuclear force, what is nuclear density. Here are some examples. Then variation of neutron charge density with radius. When the radius of the nucleus increases, and you can see in the x-axis you have r, and in y-axis you have rho, and the curve is like this. Then mass and binding energy. Nucleons are held together within the tiny nuclear volume by a short-range nuclear forces. And the energy that holds nucleon together is known as nuclear binding energy. So why this is very important? You know, like charges repel each other and the unlike charges attract each other. In nucleus, you have a number of protons which are positively charged. So these like charges must repel each other, but they are beautifully placed in the nucleus and never go out from that nuclear region. So there must be a binding energy that is responsible to overcome the repulsive force between protons, and this is nothing but the binding energy, Be. And where from this binding energy comes from? This energy is equal to the energy needed to separate the bound neutrons. From this we can say that the nucleus loses or releases some energy when nucleons are packed in, and unpacks if the same amount of energy were given to it. So this energy must be accounted for by loss or gain of some masses. So an important concept is mass defect, which you know, and I am recollecting this. Del M is equal to capital Z small m subscript P plus A minus Z Mn minus Ma, where your del M is the mass defect, Z is the atomic number, A is the mass number, Mp is proton mass, Mn is neutron mass, and your Ma is nuclear mass. So in practice, actually your atomic mass and atomic mass, as if you add the mass of protons and neutrons, and the actual mass of the nucleus is not same, and the difference is known as the mass defect. And if this is converted in energy unit, your del M multiplied by 931.5 mega electron volt, which is atomic energy unit, you have your binding energy, and this energy binds the nucleons together in the nucleus. So for your helium nuclei, that is 4 helium-2, Ma is equal to 4.00153 U, and taking the proton and neutron masses, you can convince yourself that mass defect del M is equal to 0.03035 U. which corresponds to binding energy 28.3 mega electron volt. The nuclear stability. We can plot neutrons versus protons in a nuclei. So in the y-axis, if you have neutrons, and in the x-axis, if you have protons, you can see that as the mass number increases, number of neutrons will be more than that of number of protons. If you go from a hydrogen to uranium, then after your iron, your number of neutrons increases in comparison to that of proton. So the total binding energy of nucleus increases as the number of nucleons decreases. Though the quantum of increase, the every added nucleon reduce for heavy nuclide. The stability of a nucleus is indicated by its average binding energy, that is the binding energy per nucleon, that is B by A. And the variation of B by A versus A is plotted in a different figure, and you can see your atomic mass number A versus binding energy per nucleon. So it has a sharp rise initially, then increases slowly, then decreases slowly. And you can see the peak is at around 50, which represents the atomic mass number of iron, which is the most stable element. Then in the figure you can see nuclear energy levels. From excited levels comes to the ground state by releasing energy, and from ground state excited to higher levels by observing energy. So energy levels are states of subatomic systems understood only by quantum mechanics. You can raise or lower the energy through by some certain permitted values. Your nuclear decay, mean life, half-life, so on and so forth. Then there are different scientists propose different models for nucleus, nuclear structure model, liquid drop model, your cell model, so on and so forth. So in structure model, the stability and instability of various nuclei can be understood. And in liquid drop model, the nucleus is considered to behave like a drop of liquid, and your nuclear binding energy EB can be represented as the AVA, which is your volume binding energy term, then AS, A to the power 2 by 3, which is the surface binding energy term, and your volume binding energy term subtracted to surface binding energy term, Coulomb binding energy term, and your asymmetry binding energy term and pairing energy term will give you your nuclear binding energy. Pairing term is added, which is AP by A to the power half, and is around 12 MeV. Cell model. The cell model considers a nucleus to be a potential well for the nucleons, unlike those of liquid drop model, which assumes the nucleus to be a liquid drop or water drop, in a sense that the nucleon coming in this region would be captured. However, the nucleus thus bound in this well occupy only permitted energy states defined by quantum mechanics. These energy states are called the cells that are available for the nucleons to occupy. Every cell has a limit for occupation by nucleons. Protons and neutrons occupy different sets of cells. The cell structure of each nuclei is different from others. Nuclei with filled cells have greater stability than those with small unfilled cells. This explains the remarkable stability of nuclei with a mass number or with a mass number minus atomic number, or mass atomic number equal to a magic number, that is 2, 8, 20, 28, 50, 82 or 126. Now, region for uranium and thorium series of radioactivity ending with stable lead, that is having atomic number 82 and mass number 208, is that it is a doubly magic nuclide having Z is equal to 82 and N is equal to 126. It must be understood that the observed stability of nuclei with magic number of nucleons does not imply that stable nuclei could be formed with any combination of Z and a magic A minus Z. You can see that nickel 5628 is unstable. Then Q value is an important thing. The total energy, including the mass energy, is conserved in a nuclear reaction, and the total mass of reactants expressed in energy unit plus their total kinetic energy must be equal to the total mass of products and the total kinetic energy plus energy of the photons released. The change in the total rest mass due to the reaction will manifest as a change in the kinetic energy or vice versa. So if M1 and MF are the total rest masses of the reactants and the products respectively, with EI and EF being the corresponding kinetic energies, then energy conservation implies EI minus MI C square is equal to EF plus MF C square, and this can be written as Mi minus MF multiplied by C square is equal to EF minus EI is equal to Q, and this Q is the rest mass energy or kinetic energy and known as Q value of the nuclear reaction. So if Q is positive, then it releases energy. If Q is negative, it absorbs energy. Then your neutron reactions with matter, influence of energy levels, cross sections and reaction rates, and your energy dependence. Then your neutron absorption, radiative capture, when neutron collides with a nucleus of mass A and your CN of mass A plus 1, compound nucleus of mass A plus 1 in an excited state, and the excited nucleus of mass A plus 1 and gamma ray is released from that. Then your neutron scattering, neutron elastic scattering, where neutron collides with a nucleus of mass A and the product will be A and N in a different direction. And here the total kinetic energy is conserved. So elastic scattering can also be through compound nucleus, where the reactant is neutron and the nucleus A, and when neutron is bombarded in the nucleus A, then the compound nucleus is formed, which is having mass A plus 1 and is an excited state. Then it disintegrates to a neutron and a nucleus having mass A, and neutron reappears as a ejectile and residual, same as a target, where total energy, kinetic energy is conserved. Then there is non-elastic scattering, where the reactant neutron scattered with a nucleus forms a compound nucleus having mass A plus 1, and it is an excited state. Then neutron reappears as the ejectile and residual, same as the target but excited, then de-excited through gamma, and total energy is not conserved. Here the product is a neutron, a compound nucleus and a gamma ray. Why elastic scattering is less significant in heavy nuclei, you can understand. Then neutron transmission and mean free path. Incident intensity having I0 and emergent intensity having I0 e to the power minus sigma Tx, and the target medium having thickness x, and shown in the picture. There is a transmission, there is, and the mean free path can be calculated by using the formula lambda is equal to total distance traveled by all the neutrons that survive collisions up to different depths by total number of incident neutrons. So lambda can be expressed mathematically as lambda is equal to I0 integration 0 to infinite x exponential minus sigma Tx, sigma T dx by I0, which is equal to 1 by sigma T. Now this abbreviation lambda is called the mean free path. So your mean free path is reciprocal of the macroscopic cross section, and mean free path depends on the energy and may also be obtained for each reaction. For a homogeneous mixture of several elements or isotopes, each with different atom densities, the macroscopic cross section for mixture is obtained as the sum of the macroscopic cross section of all the components. Now we shall discuss resonance. Resonance in the cross section, when seen as a function of neutron kinetic energy, are understood by using the compound nucleus model of the reaction. So compound nuclear reaction probabilities and resonances arises due to the energy levels in the compound nucleus. The compound nucleus is formed in an energy level that depends on the energy of the neutron. For a compound nuclear reaction, X, the cross section sigma X, which is a function of E, of neutron energy E, is given by the combined probability for the formation of compound nucleus sigma Cn of the neutron energy E, and the decay of the compound nucleus to the mode X. So sigma X is equal to sigma Cn Px, where energy level of compound nucleus and cross section of the resonance are shown in the screen. Compound nucleus energy levels and cross sectional resonances, neutron binding energy and neutron kinetic energy. So you can see the spacing between energy level becomes smaller at higher energy level, high level energies, thus rendering the resonances clustered or overlapped at high energy. So according to Heisenberg uncertainty principle, every energy level has a width or uncertainty. This width manifests as the width of a resonance such that sigma del T is equal to h by 2 pi. So your energy width is sigma is taken as the resonance half width, that is full width at a half maximum, and the del T represents the lifetime of the nucleus in that level. So these are the resonance curve, neutron energy in x-axis and sigma in y-axis. Then our Brett-Wigner formula. So you will know the cross-section resonance is very important for a reaction X around a neutron energy capital E, and a single level Brett-Wigner formula can be written as sigma X, which is a function of capital E, is equal to pi by k square Gj multiplied by gamma n gamma x by E minus E0 square plus gamma square by 4. Your Gj is equal to 2j plus 1 by 4 pi plus 2. And you can see that your sigma 0 cross section, sigma 0 is equal to 4 pi by k square Gj gamma n by gamma, and your sigma x is equal to sigma 0 gamma x by gamma 1 plus 1 by 1 plus y square root over of E0 by E. So your compound nucleus has different possibilities to de-excite. The fraction gamma x by gamma gives the probability that the compound nucleus chooses the mode X, and Brett-Wigner shape is a Lorentzian. It represents elastic scattering when X is equal to S by usual convention, and your elastic scattering happens through direct and compound nucleus routes, and the modified expression will be sigma S, which is a function of E is equal to 4 pi S square plus sigma 0 gamma n by gamma multiplied by 1 plus y square root over of E0 by E plus 2 sigma 0 k y by 1 plus y square multiplied by root over of E0 by E. So your 4 pi S square is the direct reaction component, sigma 0 gamma n by gamma 1 by 1 plus y square root over of E0 by E is the resonance component, and your 2 sigma 0 k y by 1 plus y square root over of E0 by E is the interference component. And your y factor in the numerator in the interference component is positive for right side of the resonance and negative for the left side, and 0 otherwise, where E is equal to E0. Similarly, S wave radiative capture and fission cross section can be written as sigma subscript gamma or sigma gamma, which is a function of E, is equal to sigma 0 gamma y by gamma multiplied by 1 by 1 plus y square root over of E0 by E. So your sigma f is equal to sigma 0 gamma f by gamma 1 by 1 plus y square root over of E0 by E. And at very low energies, Brett-Wigner formula gives 1 by root over of E, that is 1 by V variation of the cross section. The presence of direct reaction component gives a constant value for elastic scattering cross section, and these trends are observed in most cases. And the Brett-Wigner formalism is the most primitive resonance formalism and shows efficiency. Advanced formalisms like Rake-Moore formalism are presently employed. However, Brett-Wigner is the simplest and practically the best for the learner to understand the cross-section resonance. Then microscopic cross section versus neutron energy. You can see in the slide, in the y-axis you have a cross section in the unit barn, and in x-axis energy in electron volt. And for hydrogen, oxygen and iron, I have shown you the elastic scattering cross section. Elastic scattering cross section curves are given in the slide. The general trend in elastic scattering is that it is constant up to certain energy. Then there are the resonances ending up in a smooth fall, and there are also dips in front of the peaks. The constant value is due to the direct reaction component and is called the potential scattering. So potential scattering cross section, which is equal to 4 pi a square at low energies, where a is the nuclear scattering radius, and the dips are due to the quantum mechanical interference between the potential and resonance scattering phenomena. So elastic scattering is non-zero at any energy. Similarly, your radiative capture cross sections for the radiative capture or the N gamma reaction are shown in the screen for iron 56, plutonium 239, uranium 238, and for neutron alpha reaction for boron 10. So radiative capture is mostly responsible for neutron loss in a reactor in addition to leakage. The lower energy smooth cross section normally shows a 1 by V variation, where V is neutron velocity and your V is directly proportional to root over P. At high energies, capture cross section falls to significant value. High capture in materials like cadmium make them candidates for reactor control material. So neutron capture in uranium 238 and thorium-232 leads to breeding of new fissile nuclide. So your N-alpha reaction is a threshold reaction, and its cross sections are 0 at low energy. Your boron 10 is an exception, and its N-alpha cross section behaves as does radioactive capture in other materials. Hence, boron 10 N-alpha is also added. The high energy N-alpha cross section value of boron 10 makes it candidate for reactor control material, wherein absorption is the preferred reaction. So there are some examples you can have. By making a reasonable approximation, you can calculate the radiative capture cross section of a nuclide at 4 electron volt energy, and given its value at 0.04 electron volt to be 100 barns. So the formula for sigma or radiative capture cross section is K by root over of E, where K is a constant. So you know it is given that at 0.04 it is 100 barns. At 0.04 EV it is 100 barns. So you put 0.04 in the denominator, the energy is 100 barns, and your K will be 20. So by putting K is equal to 20, you can have your energy as 10 barn. Okay. Radiative capture is equal to 10 barn, your 20 by root over of 4. So you know fission, NF, low energy behavior. The 1 by V behavior of capture and fission and the constant variation of elastic scattering at low energies can be obtained from the Brett-Wigner formula. So your 1 by V behavior of the capture and fission and the constant variation of elastic scattering at low energies can be obtained from Brett-Wigner formula. So the cross-section equation may be written as sigma x is directly proportional to 1 by K gamma n gamma x by E minus E0 square plus gamma square by 4. So at very low energies, E is insignificant compared to E0. Also, E0, gamma y and gamma f are constants for a given resonance. So the total width gamma is also constant at low E. Since gamma n is very small and the other widths are constants, so your sigma x is directly proportional to 1 by E multiplied by root over of E by constant, which is directly proportional to 1 by root over of E, which is directly proportional to 1 by V, where V is the neutron speed. For elastic scattering at low energies, you have three things. The potential scattering term is constant, that is equal to 4 pi a square. For the resonance term, since gamma x is equal to gamma n, the gamma n square in the numerator and k square in the denominator, both directly proportional to E, leads to a constant contribution. And for the interference term, the product gamma n and k in the numerator with k square in the denominator leads to a constant contribution. So your low energy elastic scattering cross section is a constant. The minimum inelastic threshold is generally higher for lighter nuclides than for heavy nuclides. And for inelastic scattering n dash, there is a inelastic scattering is a threshold reaction. Beyond the threshold, the cross section increases to reach a maximum and then falls. The value of cross section is below a few barns at the peak. Inelastic scattering is more significant for heavier nuclides than for the lighter ones. As the threshold for the heavier nuclide are relatively lower, around 50 kilo electron volt for uranium-238, Inelastic scattering leaves the residual nucleus in an excited state. As there are many excited states, the residual may be left in any of the excited states. And depending on the compound nucleus excitation level, you have your inelastic scattering cross section for fast excited in manganese 55 and iron 56. Is as shown in the screen. Neutron multiplication reactions like N, 2N are threshold reactions. Neutron disappearance reaction like MP, ND, NT, N alpha are generally threshold reactions, but occur without threshold in a few cases where deuterium, your tritium, etc. The cross section curve for the threshold reactions behaves like the inelastic scattering. Such reaction, when they have threshold, are endoergic, that absorb energy with negative Q value. So you can calculate binding energy per nucleon for carbon 12's atomic number 6. The mean life Tm of a radioactive nuclide is 12 minutes. So if there are 1 million nuclides to start with, after what time would there be a 250,000 of them left? You can calculate. Gamma radiation is emitted in neutron inelastic scattering as well as in radiative capture reactors. So which of these gamma radiations have higher energy? You can calculate, and you can know why. Uranium-238 plus neutron gives rise to compound nucleus uranium-239 and gamma ray, which is inelastic scattering. And what would be the total energy of gamma radiation? You can calculate by assuming incident neutron energy negligible. And you can calculate the macroscopic fission cross section of uranium-235 from microscopic fission cross section of uranium-235, taking it as 500 barns. So you have some terminal questions. The binding energy of nucleus is given by del M plus 3 plus 931.5 mega electron volt, and your mass defect will be ZMP plus A minus ZMN minus MA, and your binding energy per nucleon will be 7.681 mega electron volt in this case, and your half life will be T half life will be 0.6931 Tm, and your Tm will be 12 multiplied by 60 is equal to 720 seconds, and your T half is equal to 0.6931 multiplied by 370 multiplied by 720 is equal to 499.032 a second. So population of given radioactive nuclide to reduce to a 250,000 after 16 minutes 38 seconds, which is nothing but 2 T half or twice the half life. And gammas emitted in radioactive capture have higher energy than those emitted in inelastic scattering, by assuming neutron considered in either case had the same kinetic energy. So these things you can go through. Okay. The reaction specified in radiation capture, your uranium-239 de-excites by releasing gamma. The incoming neutron has added its binding energy in the compound nucleus uranium-239 and its kinetic energy. So your neutron kinetic energy is negligible. The entire excitation energy is due to the neutron binding energy in uranium-239. So your gamma energy released is equivalent to the binding energy of the neutron in uranium-239. So your solution is to find the binding energy of the neutron in uranium-239, and the binding energy will be 4.80654 mega electron volt. Okay. So we shall again discuss and clarify your doubts regarding nuclear fission in the next class. Thank you. If you have any doubt, you can ask.
Okay, I think you have gone through the terminal questions and SAQs, and your nuclear fission is very much important concept which I was taught you in the first class, and now I am explaining you. If you have any doubt, you can ask. Okay, so you can go through this, and if you have any doubt, you can ask tomorrow at 6 p.m. when we shall take this class. Thank you.